Welcome everyone. Today we're going to be doing equations of motion, and I love this section. I get very excited because it just makes a lot of sense to me. So let's get going and see where we get to, okay? So, have you ever thought about how to describe the motion of an object without using graphs? So we've done graphs of motion, and we've seen how the shape of the graph helps us and how we can get things from the gradient and from the area. But what if we don't have a graph? What if we don't have that information available and we only have snippets of information? Well, what do? We use equations. Okay, so we've done all of this first part, and today we're going to look at equations of motion. Now, keywords: final velocity, initial velocity, acceleration, displacement, time, and stopping distance. There's a big thing about stopping distance, okay? So we're going to make note of that. So here we go. Let's see what equations of motion has for us. First of all, we have the equations. Now, there are 4 equations for this. The nice thing for this is that it's on your information sheet, so you don't have to remember them. Obviously, the more you work with them, the more you remember them, the easier it becomes. But please use your information sheet. You must work with the equations as they're given to you. You can't make them up. Then, we're going to look at calculations. Always the fun part. First of all, let's go through some of the physical quantities we're going to deal with. So you need to know their name, their symbol, what they are measured in, and then whether they're a scalar or a vector. If they're a vector, I need to give a direction to them. If they're a scalar, they don't have a direction. Okay? So the first one is displacement. We use delta x because we're only working with horizontal motion. Okay? It's a vector, have to give me direction. Acceleration, meters per second squared, also a vector. Now please, and this is quite important because I see it all the time, that's a lowercase a. It's a baby a. You can't make it a capital A. Capital A means something completely different, so be careful there. Then we've got initial velocity. We know V stands for velocity, but the I means initial. Initial, beginning. Okay, so initial velocity is the start of the motion. VF is final velocity, final meaning at the end. Now what's important is we can only use the equations when the acceleration is constant. If the acceleration changes, then we have to start with a new equation, okay? And then, of course, there's time. We write it as delta t, so that means change in, but we'll only give you one time period, all right? So don't stress too much about the delta. So we'll tell you that it goes 3 meters in 2 seconds. The seconds is time, delta t. Again, lowercase t, not capital. Capital T means period. It's a totally different concept. All right, so be careful. Also, because you're given the equations on your information sheet, we can't give you leeway if you've written them wrong. And if you write the equation wrong, you actually can't get any marks because you're starting from the wrong point. Okay? So, these are our 4 equations. VF equals VI plus A delta T. We're going to work with all of them, so don't stress too much. Delta X equals VI delta T plus a half A delta T squared. We don't always like using that equation because of the square, but you know what? Look at the information you're given and then decide on the equation. So don't decide right now that you're not going to use an equation because you don't like what it looks like. It all depends on the information. Then we've got VF squared equal to VI squared plus 2A delta X. And then we have this one. Now be careful with this last equation. This equation is only valid if your acceleration is constant. You are going to be very, very tempted to use this equation where you have a situation where they tell you an object moves at a certain velocity, then it accelerates, then it gets slower, and they want to know the distance that it moves in. But meanwhile, from start to finish, the acceleration has changed more than once. You're going to be very tempted to use this equation. You can't. Acceleration must stay constant. Now, I tend to not use that equation because there's not many places at the moment where we can use it. When we look at vertical motion, this equation's great because vertically acceleration stays the same. So, the conditions for our use of these equations. The movement, it must be in a straight line. We are working with linear motion. Please be careful. There are situations, for example, if you have a pendulum, which is something that swings backwards and forwards, okay? Here, we're going to be very tempted to use an equation of motion. And you know what? You'll get the right answer. But this is circular. It's not straight. Linear means straight line, okay? Linear means straight line. Very, very important. And then constant acceleration, including no acceleration. If there's no acceleration, acceleration is zero. It's fine. Okay, so that makes it easier. You have to remember those two conditions. So, time for a short break, and I'll see you in a couple of minutes. Welcome back, everyone. I hope you had a good break. Let's just get straight into it, shall we? So, what we're going to investigate now is how those equations of motion we just looked at are related to graphs. Because I said we can use them instead of graphs, but sometimes we just need to see the connection, okay? So what we're going to look at is we've got this. We have the position time graph for a cyclist that is moving west. So we know he's going west, and what this is telling me, original displacement, that's where he's starting from. He moves 50 meters, then he stops for a little bit, and then he goes 50 meters backwards, basically. So, first thing is, we would say to you, calculate the velocity at 4 seconds. Now, because the displacement time graph is a straight line, we would say, well, what is his velocity during that point? And we remember from graphs that to get velocity, we would use the gradient. So we would go, his velocity is the gradient of my graph, which, oopsie, maybe I should spell gradient correctly for you, because that's not it. There we go, gradient, which would be change in displacement over change in time. So we would go, the displacement is 50 minus 0 over 4 minus 0. So we've got 50 divided by 4. And of course, we take our calculators and we get 12.5, okay? So 12.5 meters per second. So that's using the graph. So now, let's look at what happens if I use equations of motion. Now, to use equations of motion, I need to decide what information I have. So, we always write down a list. So VI, VF, VI, we've got A, delta t, and delta x. Now, it's going at constant velocity, so I know acceleration is 0. My time to get here is 4 seconds. My distance is 50 meters. The issue is that I want VF, okay? So when we think of the equations, we've got a few that we could use, because we've got VF equals VI plus A delta T, but A is 0, so that's not going to help me. We've got VF squared equals VI squared plus 2A delta X. That's not going to help me. Then I've got delta X equals VI delta T plus a half A delta T squared. So when we look at this, I know that VF equals VI plus A delta T. We've just said that A is 0, so this is what happens here. So when we take this, this is going to be 0 times 4. This is very important for me to take note of, because what I'm now telling you is that VF equals VI. How do I know that? Well, it's a straight line on the displacement graph. So velocity is constant. This is very, very useful for us. So I'm going to go back to my equation, and what I'm going to do here is, instead of putting a question mark there, I'm going to say, well, let's make VF and VI equal V. They're the same value. I can now choose a better equation, not using acceleration. So what I can use instead now is, if I go back to this equation, that delta X equals VF plus VI over 2 times by delta T. I know that delta X is 50. I have now said that VF and VI are both V, so this is V plus V divided by 2 times by 4. Okay? I'm going to divide by 4 on both sides straight away. This is going to become 2V over 2. That's nice, because the 2's cancel out. And if you look carefully, I've got 50 divided by 4, and I had 50 divided by 4, which means that velocity is 12.5 meters per second, which is exactly what I got when I used the gradient of the graph. Okay? So the key was to remember that VF is equal to VI, because the acceleration was 0. Now I know in your head you're going, but it started at 0. That's only when we started timing. I didn't tell you that the cyclist was stationary. The cyclist was moving, okay? So he was already moving, then he passed a point, we started the stopwatch, and we saw what happened after that. I don't really care how we got to the 4, or the 12.5, it doesn't matter, okay? So, now they want the velocity between 10 and 18 seconds, okay? So this is where the 10 is, 2, 4, 6, 8, 10, that's 12, 14, 16, 18 is here, okay? I know it's hard to see. Now, here, we were looking, again, we would use the gradient of the graph, okay? So we would go, we want V, we're looking at the gradient, okay, and his gradient is change in x over change in time. So we're going to go final, which is minus 50, minus initial, which was 50, and it's going to be 18, because it's 18 seconds minus 10. All right, so we're going to use our calculators, and we get minus 50, and we're going to divide that by 18 minus 10, and it's minus 12.5. Now, if I asked you to solve this using equations of motion, this now becomes interesting for us. Oh, and before I forget, this means that it's 12.5 meters per second east. He was going west originally, okay? And we've got a negative value. I would ask you to go, what is his velocity at 18 seconds, okay? The same thing applies as what we just did in the last question, which I know feels a little strange now because in the real world this wouldn't happen. Over here, between 4 and 10, he's stationary. He hasn't moved, okay, because his displacement stayed the same. Then we've got an instantaneous straight line. So what the graph is telling you is he went from stationary to 12 meters per second, 12.5, sorry, instantly. There was no acceleration. We know that can't happen. It doesn't matter, okay? But what we do know, because that's a straight line, is his initial velocity and his final velocity are the same. So I can do exactly the same as I did in the last question. Delta x, Vf plus Vi over 2 times delta t. The issue now is what is delta x? Okay. 50, he was 50 meters away from the start, 50 meters in the other direction. So if I had to draw it, like, here's where it starts, he was there, then he went there. So his displacement is 100 east. In other words, this is minus 100. Okay? We know that the velocities are the same. And the time, it's from 10 to 18 seconds. So that's 8. So we're going to have minus 100 divided by 8, 2v over 2. The 2's cancel. So again, we take out our calculators. And I've got minus 100 divided by 8. And I get, there we go, exactly the same answer. But we've got to have it as a positive. So sometimes the graph is easier, but a lot of the time, equations of motion are better, okay? Because it gives us an easier way to work things out, okay? So let's do another one. So now we've got a velocity time graph, okay, and it's going north. So here we go. We want the acceleration. Now, this is fun. Acceleration for the first 3 seconds. Here we go. Acceleration from this graph is the gradient. So gradient is my acceleration. So that's change in velocity over change in time. So we've got 60 minus 0 and 3 minus 0. And, of course, we use our calculators. 60 divided by 3 is 20 meters per second squared. Okay, and it's north because it's positive. So this is where the equations become nice. Final velocity, 60. Initial velocity, 0. Acceleration is what I want, and it takes 3 seconds. Well, watch. First equation, Vf equals Vi plus A delta t. Vf is 60. Vi is 0. We want A, and we know it's times by 3. So I'm going to divide by 3 on both sides. Right, so A is 60 divided by 3, which we know is 20, and it's going to be 20 meters per second squared north, because it's positive, okay? Let's try one more just to check that we're doing it all right. Now they want the acceleration in the last 3 seconds. So that's this part. Okay. Last 3 seconds, again, we start on the graph. So let's say we know that acceleration is the gradient. And that's change in velocity over change in time. In this case, the velocity, final velocity was 0. Initial velocity was minus 60. My time was 11 minus 8. Okay, so let's put it on the calculator. So I've got 0 minus 60 divided by, okay, let's first answer it, divided by 11 minus 8, and I get 20, which I'm happy with because it means, maybe I should actually have a pen. There we go. So it's 20 meters per second squared, and it's north, and I'm happy with that because it's a positive gradient. Let's do it with equations of motion. So VF is 0 because it stopped. VI is minus 60 because it's over here. We want A, and my time is the difference here. So it's from 8 to 11, which we know is 3 seconds. We're going to use the first equation. So VF equals VI plus A delta T. VF is 0. VI is 60. We want A. It's times by 3. So if we take the 60 over, it becomes positive 60. 3A, we're going to divide both sides by 60. So A is 60 divided by 3, which we've actually already worked out. So that means that this is 20 meters per second squared. And because it's a positive value, I know that that is going to be north. So to get A on its own, we're going to have to divide both sides by 3. We know already that that's going to give me 20. So it's 20 meters per second squared north, and that's exactly what I got when I worked out the gradient. Well, that's all for now, guys. It's time for a short break. Go get some water, and I'll see you in a couple of minutes. Welcome back, everyone. You ready to get stuck into some nice, juicy questions? Let's get going. So, when we start these, we need to have some idea of where we're going with these problems, okay? So these are some tips. These are just things to keep in the back of your mind so that you can make sense out of the questions, okay? First one being, write down everything that you've been given, okay, with the correct SI units. Then write down what you have to calculate. Put a question mark by it. Then you choose a direction as positive. This direction as positive is beyond important, and you have to keep it. I suggest that you actually write it down. There's no marks for making this choice. But if you don't write it down, you forget it. And then along the way, your signs get muddled, and then your questions are wrong, okay? You must choose the most suitable equation of motion, and we've got 4 to choose from. Substitute in the values. Don't substitute in the units, just because it gets very messy. These are quite complicated equations, so if you've got all the units in it, it just gets messy. Just use the numbers, okay? Then do the calculation. Then remember, big NB. Direction. If you have calculated a vector, in other words, velocity, acceleration, or displacement, I must have a direction, okay? If you've calculated time and you got a negative answer, you've made a mistake. Start again, okay? If you are only asked for magnitude, then you do not need to give me a direction at the end, but you do have to make sure you give me a final answer that's positive. So if it's a velocity and you get minus 20, for example, you need to do one more line where you go, the velocity is 20 meters per second, okay? Magnitude means I want a positive final answer, but I don't need a direction. All right, so let's look at some questions. An aircraft accelerates from rest. Initial velocity is 0. At 9 meters per second squared, so that's A, down a runway, and they want to know what the velocity of the aircraft is, VF, after 50 seconds. What I've just done while I'm reading the question is really what you should be doing. This is a fairly simple question, but you need to get into the habit of when you read your questions, picking out the important information. Highlight it, use a pencil, use a pen, because when now I go to my question, to my answer sheet and I write it down, I've already got highlighted the information I need from the question. It makes it a bit easier for us, okay? So, I always write my list in this order. And if you look very carefully, this first part is actually from the first equation. VF equals VI plus A delta T. Then I just put displacement at the bottom. So what did I know? A is 9 meters per second squared. And they said the aircraft's velocity after 50 seconds. And I want VF. And I can see from there, because I want an equation that doesn't have delta X in it, it's going to be the first equation, which we then write. And by now we know that one because we've used it lots. I want VF. I know VI is 0. A is 9, T is 50, and of course we need to put this on into our calculators. So 9 times 50, 450 meters, well, 450 meters per second. Now we've got to talk about direction. I can't say left, right, up, down, north, west, because they didn't give me that. They just simply said the aircraft was going down the runway. That's how I describe my direction. Down the runway. That's fine for a direction because that's how they gave me the direction. I could have said forward. That also would have been fine because we're assuming the aircraft's going forward if it's going to lift off. But what we need to remember here is that I can't give any other way than the way they gave me the direction. So how they describe direction is how I describe the direction. And particularly when there's no diagram, you have to get it from the writing, from the question, okay? Let's do another one. So here we go. A minibus is traveling at 12. Initial velocity. The minibus needs to stop the final velocity is 0, and it's got 30 meters to stop in. That's delta x. Now they say calculate the minibus's acceleration if it is to stop in time. They don't give me time. They want acceleration. So, let's see. We're going to start with writing down what we know. Okay, VF is 0 because it's going to stop. VI is 12. Acceleration is what I'm looking for. They didn't give me time, and I know it's going to do it in 30 meters. We now need to go through the list of equations, and we find the one that doesn't have time in it, because we don't have time. I know that that means we're going to use this equation. VF squared equals VI squared plus 2A delta x. VF is 0, VI is 12, plus 2 times A times 30. At this point, if you can solve for A straight away and you don't need to show all the maths, go ahead and do that. But I think it is safer for you to do all the maths so that when you go back to it, you can see if you made a maths mistake, because that's sometimes where the wheels fall off a little bit, okay? So I'm going to do all the maths. So I've got 0, 12 squared, wrong one, there we go, is 144. So that's 144, plus now it's going to be 2 times 30, which is 60. I'm going to take the 144 over, so it becomes minus. Now I need to divide by 60 on both sides, but remember this is now minus 144 divided by 60, and I get minus 2,4. We never ever leave an answer as negative. I've got a negative acceleration because it was slowing down. I expect that. So now I've got to think about what the direction's going to be. Remember, the minibus would have been going forward. So my acceleration is backwards. That's very important here. I now need to say my acceleration is 2,4 meters per second squared backwards. Okay? The direction here is very, very, very important. Don't forget it out. Acceleration is a vector. If I need to use this acceleration, so if there's another part to the question, and I need to use this acceleration, I'll substitute in the negative value, because it is negative. But when I describe it, I use it as a positive value with a direction in words. You never have a negative value with the direction in words, ever. You cannot do that, okay? So, okay, we need a short break, and when we get back, we'll do some slightly more complicated questions. I'll see you in a couple of minutes. Welcome back, everyone. Let's just dive right into some questions that are slightly more difficult, okay? So, here we go. A car starts from rest. Now, you can see there's a couple of things to here. So, we've got a car, starts from rest, so VI is 0. accelerates uniformly, which is what we work with, along a straight road at 4, so that's acceleration, for 4 seconds, so that's delta t. It then, there's a second part. It then continues at constant velocity for another 7 seconds. So at this point, a equals 0. There's 2 parts to this. First thing they want is the velocity, Vf, of the car after 4 seconds. And then the total displacement of the car for the whole 10 seconds. It's actually 11 seconds, so let's change that to 11, because 7 plus 4 is 11. Right, let's start with the first part. We know that we're going to do this. So we have our list. Okay, Vf is what we're looking for. Vi, they started from rest, so it's 0. They told me it accelerates at 4 meters per second squared, and it does that for 4 seconds. That's the first part, okay? It then continues the second part. They want the velocity, so I want Vf. I'm going to choose the equation that doesn't have x in it, because I don't know delta x. Therefore, Vf equals Vi plus a delta t. Vi was 0, a is 4, time is 4. So we take out our trusty calculators, and we get 16. So it's 16 meters per second, and I'm just going to say forward. That first question was nice, very nice. Straightforward, nothing to worry about. Now they want the displacement over the entire 11 seconds. Now this is what you need to be careful of. You are going to be very tempted to use this equation. Okay? You're going to be very tempted because you're going to go, I know a Vf, we just worked it out, it was 16. I know a Vi, it was 0. And I know a time, it's 11. But remember, this is only valid if the acceleration stays constant, which it doesn't. You have a 2-part journey. One part of the journey is when it starts at 0. It travels for 4 seconds. It has an acceleration in those 4 seconds of 4 meters per second squared. Then, and it gets to 16 meters per second here. Then it goes for another 7 seconds, and this acceleration is 0. Acceleration changed. If the acceleration changes, I have to work out the displacements separately. I can't do it together. So I'm going to need to go, what is this first displacement? What is this second displacement? The thing to remember is that this velocity is the same. So that stayed constant. Okay, so let's do the first one. So for the first motion, so this is for the first 4 seconds, Vf is 16, we worked that out. Vi is 0. A was 4. Time was 4. And I want delta x. So right now, you can actually use any of the equations because you've got so much information. Choose the equation that's going to make life easiest. So what I would do is use this equation, delta x Vf plus Vi divided by 2 times delta t. And we're using x1 here. So 16 plus 0 divided by 2 times by 4. Okay? So let's do it on the calculator. So we've got 16 plus 0 is 16 divided by 2 times by 4, and we get 32. That's the first part. Now we need to do the second part. Vf is 16 because there was 0 velocity. Vi is 16 because that's what we calculated. A is 0. Delta t is 7 seconds this time, and I want delta x. I'm going to use exactly the same equation. That's okay. So, and this is x2. So Vf plus Vi divided by 2 times delta t. So 16 plus 16 divided by 2 times by 7. Oops. There we go. 16 plus 16 equals divided by 2. That's 16 times by 7, and it's 112. But we're not done because the question wanted the total displacement. So the last part is I'm going to go my total is my x1 plus my x2, 32, plus 112. And just to be on the safe side, we use our calculators, and we get 144 meters forward. Okay? Because the acceleration changed, I had to do it in 2 parts. Okay? Very, very, very important here. A cyclist is training for a race when a car suddenly pulls out into his path. The moment he saw the car, he braked hard to avoid crashing into it. Very important. His speed decreased from 15, so that's initial velocity, to 3, final velocity, in 3 seconds time. Calculate his acceleration, that's the first one. Then they say if he continued at the same acceleration while the car is 1.5 meters away, would he have been able to stop in time? So, let's calculate his acceleration. Vf is 3. Vi is 15. A is what we're looking for, and they say he does this in 3 seconds, okay? We don't know delta x, but we don't actually need it because, again, we're going to use the first equation, which we've done lots today. Okay, so Vf is 3, Vi is 15, A is 3. So now we need to be careful. So I'm going to take the 15 over, so it becomes 3 minus 15 equal to 3A. And then I'm going to divide both sides by 3. Okay? Now I'm happy that I'm going to get a negative answer here. All right, divide by 3, and I'm going to get minus 4. That's fine, because he's slowing down. But remember, we don't leave it as a minus, so that means his acceleration was 4 meters per second squared backwards. Okay, that acceleration is what he's got for the whole journey. Now they want to know if the car is 1.5 meters away, would he have been able to stop? So his initial velocity, they want a final velocity of 0. So there's a couple of ways you can do this, but I'm going to show you the easiest. His initial was 15. His acceleration is -4. Okay, we don't know how long it takes him to stop, but they do tell you that he needs to go a distance of 1,5, and if he stops, he needs to be at 0. So either I've got to show this value, or I've got to show this value. And it's easier to find his stopping distance. So what I would do is go Vf squared equals Vi squared plus 2a delta x. We know he needs to stop. Okay? We know that he was going at 15 meters per second squared. That's -4. Okay, so this becomes minus 15. Oops, you know the minus should be in the other place. It should be outside the bracket. Give me a second. Okay, and that's -8. So on my calculator, I'm going to go 15 squared. Okay, and I'm going to divide that by 8. And I get, he's not going to stop in time. Because what do we get? We get 28,13 meters. Okay, which is bigger than the distance he had. So he won't stop in time. Okay, not a chance will he stop in time. But now we have to stop. So I'll see you again next time.